Hello, in this video we're going to talk about how to make a cobweb plot with pencil and paper. In another video we'll talk about how to do that in MATLAB. So the key to success here is do not pick up your pencil from the paper at any point in this process. Alright, so you've got 4 steps and the last 2 steps are going to repeat indefinitely. So step number 1, we're going to begin with an initial condition x0, and that's going to be on the horizontal axis. Number 2, you're going to drive up to hit the curve, and in this picture the curve is drawn here in purple. So this is our iterative map, this is our relation, and you're going to then drive right or left to hit the line y equals x, and the line y equals x is drawn here in black. And then step 4, you're going to drive up or down until you hit the curve and repeat over and over. Let's do an example. So let's start with our initial condition. Once we have our initial condition, we're going to drive up until we hit the curve. Next, we drive left or right until we hit y equals x. Next, we drive up or down till we hit the curve. Next, we drive left or right till we hit the line. Next, we drive up or down, left or right, up or down. We keep repeating this process. And what ends up happening is our movements get so tiny, we end up at a fixed point, and this is a stable fixed point because it's absorbing our movements over time. Let's do another example. Let's make a cobweb plot for x sub t equals negative 0.3 x sub t minus 1 plus 2. And we'll start with an initial condition 0.5. Okay, so first of all, how do we plot this particular recurrence relation? Well, if we're going to plot it in a plane that has x sub t minus 1 on the horizontal axis and x sub t on the vertical axis, that's essentially saying, you know, how would you plot the line y equals negative 0.3 x plus 2? Right? This is like a y equals mxb plus, this is like a y equals mx plus b situation. And we recall from graphing, this would have a y-intercept of 2, and then it would have a pretty shallow slope going downhill, something like that. Alright, and I've drawn that already here with the purple line. We want to start with our initial condition, which is 0.5. And remember, the idea is we're going to go up and down, then left and right. So we'll go up to the curve, then we'll go left or right over to y equals x, then we'll go up or down till we hit the curve, then we go left or right till we hit y equals x, then we go up or down till we hit the curve, then we go left or right till we hit y equals x, and we keep this process going. And once again, we find that we have a stable fixed point because our movements get absorbed by that point over time. Now, if you wanted to, you could also analytically find where the fixed points are. You could do a fixed point analysis, and from our previous video we learned that we would set x sub eq equal to negative 0.3 x sub eq plus 2. Adding a 0.3 x sub eq to both sides, we find that on the left hand side we have 1.3 x sub eq equals 2, and solving for x sub eq we get 2 divided by 1.3, which equals 20 over 13, and we can see that exactly right here in the picture. Okay, so there's our fixed point right there, and the fixed points are always where the curve intersects y equals x. The fixed points are always the intersection of y equals x and your curve, which represents the recurrence relation. Okay, let's do one additional example. Let's make a cobweb plot for x sub t equals 1.5 x sub t minus 1. Now, up until this point we've been drawing our cobweb plots in a box, but they need not always be done that way. You could certainly start off in the xy plane, and in this example I'll do that. This curve is essentially like plotting y equals mx plus b where y equals 1.5x minus 2. And the reason why I'm making that connection is because our horizontal axis instead of x is x sub t minus 1, and the vertical axis instead of y is x sub t. So I've just relabeled things and viewed this through the lens of a slope-intercept form of a line. Okay, so I've got a y-intercept of -2, so that's somewhere down here. And that's roughly a good plot. So let's clean up our drawing a little bit here. And let's begin with an initial condition. Let's start over here somewhere. What happens when I start with this initial condition? Remember, I'm always going to drive up till I hit the curve. Not y equals x, but I'm driving up till I hit the curve. And so in that case, I'm going to drive up till I hit the curve. Then I drive over to where I hit y equals x. And then if I extended my curve even more, I would be going up and over and up and over indefinitely. What happens if I start over here somewhere, x naught? Well, I would drive up till I hit the curve, over to y equals x, up or down till I hit the curve, left or right till I hit y equals x, up or down till I hit the curve, left or right till I hit y equals x. And again, out and out I would go. This fixed point in this picture, this is a repelling point or an unstable fixed point. My movements are repelled away from it. And no matter where I start, I just go away and away from that fixed point.